that I throw this stone low speed, you know what's gonna happen? The stone's gonna land here, right? Low speed.
Yeah.
If you go for a higher speed, it's gonna land here. The stone's gonna land here if you throw it so faster, right? So you see what's happening? Okay. What if I throw it harder even? What could happen?
Yeah, at some point it's gonna come out.
At some point, you're just gonna make this
It's gonna come
go.
out of the. It's gonna.
There are two ways. There are two ways that's gonna happen. Two things rather that's gonna happen, right? One is this. Eventually, you're gonna go around like that, right? Or if I use blue, and it won't come back down, but it hasn't escaped.
Yeah.
It's still there. Or the other one is you're gonna throw it so hard that it basically goes in a straight line, right? Okay, I'm not gonna do that like that because that could still come back. But the idea is you throw it so hard, it goes that way. Okay, what's your question here?
But we said the further away you are, the slower the velocity, right?
Yeah, the idea is this. Okay, then okay. I think I'll do another person. This time it's me. Yeah. Instead of throwing the rock horizontally, I'm gonna throw my rocks vertically. Yeah. What if I throw the rock with a slow speed? With a low speed, it's gonna go up. It's gonna be that way, right? But because the velocity is low, it's gonna go back. But what happens as it goes up? It slows down, right?
Yeah.
Okay. If I throw it with a higher velocity, it's still gonna go up, slowing down as it does, and then goes back down. Come back down, right? But the idea still is, as it goes up, it slows down. We hit a point wherein it stops. Right? Okay. What if I throw this rock really hard?
It stops slowing down?
Well, okay. So I'm gonna zoom into this flat section right there. Yeah. So again, if the velocity is low v, it's eventually gonna hit this point. In this point, v is equal to 0. Then it's gonna come back down. Right? So here from a low v to 0, so you can actually assume that there's slowing down happening here. There's deceleration, right? Now similarly, if I have a very fast stone, it's gonna go that way. Eventually, it's gonna follow the same general idea. There's still this point wherein the velocity is 0, and still from this region to this region, from this time to this time, it slows down. It makes sense if you think about it just on Earth, right? But if you think about this is the r.
Yeah.
This is a small r. This is also the another r. The distance that it has to travel. So the idea now is how fast do I need to throw this stone so that it doesn't come back. Okay. So how fast must the stone go so that it doesn't come back? Doesn't come back. To be specific, I'll change that how fast it to what is the minimum speed to throw the stone. Okay, so that it doesn't come back. And this minimum speed that that we can calculate is the terminal velocity. Okay, stone. Okay, but here's the thing. I can also ask this question right here. What's the minimum speed to throw the stone so that it doesn't come back? But this time it's a horizontal throw. Right? You get it?
Yeah.
Vertical throwing, this is another way of looking at it. Vertical throwing is therefore the escape velocity. Okay, velocity. Horizontal throwing, on the other hand, if you look here, the stone doesn't come back, but it doesn't really escape, right? It stays within the gravitational influence of the Earth. So this is where horizontal throw, this is going to be the orbital speed. You get it now?
But okay,
But-
I start getting it just for the vertical throw.
Uh-huh.
How is this? Oh, it never truly escapes. That's what we said before. That's why it will come back down to Earth.
It will again, the only time that it will truly escape is if it goes an infinite distance away from Earth.
So wait, let's say we have the sun because it's way stronger.
Yes,
the pull
yes,
is way stronger,
good.
right? Okay, so there's no other planet in the universe. Like it's only the sun.
Uh-huh.
And we would throw something very far away. It goes really, really far away.
Yeah.
But it doesn't. It nearly reaches zero, but it doesn't reach zero. So that means at some point, even though it's billions of kilometers away, it would come back.
Yes. However, that's assuming the only bodies are the sun and whatever was thrown, right?
Exactly. Well, now it makes sense because there's other planets attracting the thing. But that makes total sense.
But that also means if you want to stay within the solar system, you have to make sure your speed doesn't exceed the escape velocity for the sun. Okay?
Yeah.
All right. But what happens? Let's say
when-
let's say that this is like imperfect, like you have these planets going around. Then, as you said, you can throw something at a particular speed and just make sure it gets to the orbit of that planet. So if you want to throw something from the sun to the Earth, you just have to make sure that you throw that object at the right speed so that we hit the orbital speed of the Earth. Eventually, it's going to come to Earth.
And
Okay.
it's gonna be stuck in Earth.
All right. So, okay, and then this horizontal thing, the horizontal throw, it kind of makes sense now because the path has to curve around, right? Okay, so let's go back to the problem earlier. So what's the escape velocity for the Earth? Sorry, not that. It's already
Oh,
here.
yeah.
So
Let me
all you have to
calculate
do now is plug the values in. You just plug this in, g. You plug the radius in, and you plug in the mass of the Earth.
So when they sent the robot to Mars, they had to take into consideration the orbits of the different planets.
Yeah, they had to
Or-
time the launch so that when the probe or the lander would reach Mars orbit, then Mars would actually be on that point of the orbit. So the launch has to be timed perfectly. Not necessarily to the second though, but maybe to within the day.
Okay, yeah, that makes sense.
Okay.
And what's the closest planet to Earth again?
It's Mars actually. When it gets closest.
Oh, it's Mars. Okay, it's because then it's easier to send something. Like if you would have to send something and go through another planet first, that would be hard because you would have to take into consideration that you would get sucked in by the other planets, right?
Good. That's
if
right.
you want to go past that planet.
There are exceptions to that rule, but generally, yes. You don't want to get stuck in the gravity of another planet. But again, there are exceptions to that. It's related to momentum. But we won't explore those yet.
Yeah. I was just wondering.
All right.
So I got I'll write the number.
Okay.
So it's easier. It's 3, 5, 3, 6. Oh, I'll just make it 3, 6. Wait.
Uh-huh.
It's 3, 6 fix.
Did you take the square
There you
root?
And it's in joules.
No, it's velocity.
Yeah, I
so
did the square roots.
Okay, let me double check.
Oh, velocity, yeah.
6.67.
I think it's this, yeah. 2 times 6.7. Yep.
Okay, let me
Yeah.
just calculate that myself. I actually know the answer, but let me see if we can get the value from here. Okay, times mass